what we'll be doing today is a bunch of this. The things that have checkboxes right next to it, we'll be trying to do today. What doesn't have checkboxes, we'll most probably be doing tomorrow. We most probably have to do ASGs also tomorrow, or the implementation of ASGs. What is an ASG? An auto scaling group. This probably will be done tomorrow because my AWS account has limitations as to how many machines I can create. And I've sort of used it to peak. I've requested for an increased limit. I don't think it has happened right now. So we'll have to do this tomorrow. And most probably these two also we'll be doing tomorrow. The rest we'll try to cover today. Where can you find the slides? You can find the slides at the end of projects.100xdevs.com. In this section called horizontal and vertical scaling, indexing in databases. That is what we'll cover this week. Basically some advanced concepts in scaling, some more advanced concepts in databases. We'll also cover a little bit of Rust to show how it's, better than Node.js. Specifically, when you want to scale, what makes it. So Rust is 10 different things, like it's memory safe, it's faster, but what makes it scalable? Node.js is very inferior when it comes to a comparison with languages like Java, Rust, Golang, because these can spin off multiple threads. They are multi-threaded. What is Node.js or JavaScript? Single-threaded. So we'll try to do some coding and implementation and try to see whether the other languages are better. We'll understand about the cluster module that pretty much lets Node.js get close to the capabilities of Golang or Rust. Let's say not very close. Like there is a difference between multi-threading, the way it is done in Golang and Rust, and the way we'll be hacking it on today. And one way to hack away, using multiple threads in JavaScript is using the cluster module. So we'll spend some time there. We'll understand what is horizontal scaling. Then we'll understand what is vertical scaling. These should actually be flipped. Vertical scaling should come here. Horizontal scaling should come here. And auto scaling groups, which let you horizontally scale on AWS. Most clouds will have some construct to let you create auto scaling groups. What does auto scaling groups mean? Means a bunch of servers that you can describe. If the CPU usage goes above 50%, please increase the number of servers, auto scale up. And then if the CPU usage goes very low, like 10%, then auto scale down. We'll talk a bit about capacity estimation, which is, just a buzzword and a system design question. A lot of times they will ask you, okay, estimate the number of videos that are uploaded to YouTube every day. How do you do that? Mental math. Load balancers, probably not today. When we understand ASGs, is that we'll understand load balancers and a bunch of other constructs that are used to create an auto scaling group. Indexing we'll cover today. Normalization and sharding we'll cover tomorrow. Yeah, that's pretty much it. The interesting bits here, I would say, are, probably this ASGs and normalization. Everything else should be fairly straightforward. Cool. That's enough context for today. Let's get into it. Let's kick things off by understanding vertical scaling. I actually want to start with a poll. Okay, how many of you already understand this? But either via first principles or you've heard of it. Do you know what horizontal and vertical scaling is generally? Most of us do. No, most of us don't. Sorry. 50-ish. Okay, so half of us know, half of us don't know. It's very obvious once you think about it. What does vertical scaling mean? Maybe even before that. Why do you need scaling? If your application gets a lot of load, then you need to scale up. It's not necessary that your application, look at that. This is what we'll be covering today. If this is your, AWS machine, EC2 machine where you're running a Node.js process, let's say node index.js. This can be used by a lot of people, not just one. Do you think an application like Swiggy is used by only 10 people? No, it's used by millions of people. So you need to somehow make this process very powerful. You need to say, take as many resources as you want. Here, take, more CPUs and more, let's say, theoretically GPUs or more memory, whatever you need, more file system. I will give you as many resources as you want so you can handle these requests. When you increase the size of an EC2 machine to do this, when you move from, a C5.x large machine to C5.4x large machine, what does this transition mean? What is C5x large? It's just a machine type in AWS. If you're ever in AWS, if you're ever in AWS and try to create an EC2 instance, it asks you, what is the size of the machine you need? The bigger the size, the more that you have to pay. So if you're scaling this way, if you're like, yeah, I'm going to expect a lot of load, let me increase my size to be not micro, but the biggest machine that exists over here. Let's say 𝗠𝗫𝗄𝗃 metal, which, is $4 per hour. How much is that in a day? 24 into 4, like $150 a day, which is how much? $4,500 a month, if the math is right, somewhere in that range, right? 3-4 lakh rupees a month. If you feel like, yeah, we are going to have a lot of load. Swiggy doesn't care. If an application like Swiggy is making millions, why would they care if getting a big machine helps them handle the load? So this is what vertical scaling means, because you're vertically increasing the size of the same machine. If this was your machine first, it only had 1 CPU. Now it has 20 CPUs. If only had 8 GB RAM, now it has 32 GB RAMs. So you're vertically scaling a machine and trying to you're hoping that your Node.js process will, be able to handle more requests if you vertically scale a machine. But do you think that is possible? Do you think that is necessary? Okay, if you vertically scale a machine, if you keep adding resources to the same machine, the Node.js process is able to handle more requests. What do you think the answer is? Do you think it is possible for your Node.js process to handle more load if you vertically scale your machine? And 50% say yes, 50% say no. The answer is no. You can say yes, something might happen, it might have more memory. If the Node.js process uses a lot of memory, then sure, increasing the size from 8 GB memory to so much memory might help the Node.js process. But specifically for processing, specifically for running for loops, if there is an expensive operation here that's happening, that's being handled over here, where does all of this run? This runs on a CPU, central processing unit. And what did we keep saying again and again? We said JavaScript is single threaded. What does being single threaded mean? It means it can only utilize one of these CPUs. It does not matter how much you scale your machine. You could have 4 vCPUs, you could have 8, 16, 32, 64. There is no point of making your machine beefier and beefier if all you are doing on that machine is running a node process. Node cannot take the benefit of all of these CPUs. It will still run on a single CPU only, irrespective of how big you make your machine. So Harkirat, should I just go with a very small machine then? Yes, unless it's going to use a lot of memory. The only problem that might come in a very small machine is, some build process is not able to happen because the CPU is not, you need like more than one threads for it. What do you mean by build? Converting, JSX to JavaScript. If you compile your React project, a lot of times on, a T2.micro machine, which a lot of you might be using if you are using the, free tier over here. The T2.micro runs on, it says free tier eligible. So we've recommended again and again, if you're starting a machine, please start it here. Running the Node.js process here is fine. It only has 1 vCPU. Doesn't matter if it has 1 or if a different machine has, 32. That is fine. They will still perform similar, not exactly the same, but very similar. It won't linearly grow for sure. If there is 1 CPU and you make it 32 times bigger, you are paying 32 times more money. Doesn't mean you get 32 times the performance. You might get 1.1 times the performance. Something extra you might be able to squeeze out here and there in a bigger machine, but not linearly. The downside is that some build process might not be able to build over here. Your machine might run out of CPU memory. I cannot build your React project. But if it's a single Node.js process, then just throw it on a micro machine, a mini machine, it'll work. Then the question is there any point of doing vertical scaling in a Node.js process? Vertical scaling means increasing the size of your machine to support more load. What does increasing the size mean? Doesn't necessarily mean increasing the hard drive. It means increasing the memory. It means increasing the number of CPUs you have. For example, if this is a Node.js machine and this is my Mac machine, this is a Node.js file which I run by running node-index.js. It doesn't matter how many vCPUs I have. My current Mac, I have 10 vCPUs, but my Node.js process will run on a single one. Does not matter how much load it's getting. Does not matter, what optimizations I do here. It can only be handled by a single processor or a single CPU because it's single threaded in nature. It has a single thread that's, going into an async function, an express handler, wherever it's going, there's no way to parallelize it. You can't really split it. You do this part, you do this part, you do it on thread 1, you do it on thread 2. You cannot parallelize, which means Node.js, not the most effective way to scale it is vertical scaling. You can try, but you will see diminishing effects. After a point, you will see no effects. So if you have a Node.js process, no point renting a very beefy machine, rent a small machine, you'll get the same performance. This is in stark difference to multi-threaded languages that do let you use all the cores of your machine. What are good examples of these languages? Java, Golang, Rust. If you have done Java, you might have created a thread pool over there. If you've done Rust, you might have spawned threads over there. If you've done Go, you might have heard of something called subroutines that let you create small routines that can be run on different threads. What do all three of these let you do? They let you parallelize. They let you be like, you run here, you do this task, you do this task, you do this task, so on and so forth. And why is this useful? This is useful because if you have a beefy machine, why do you want to keep so many cores idle? Why do you want Rust, you only run over here? I will only give you, 1/10 the power that exists on this machine. You don't want that. And hence, you can write code in a way. You have to write code in a way. It's not as easy as, I will create a for loop and it will get parallelized to all of these cores. No. If I give you a problem statement that says, find me the sum of all the numbers from 1 to, let's say, 1 million, or some big number like this, and you write a for loop. Okay, I will do this for let I equal to 0, I less than very big number, I plus plus, answer equal to answer plus I, and then, console.log answer. If you do this, or if you write similar code in Rust, Golang, or Java, all of them will be able to compute this on a single thread only. Right? Writing multi-threaded code isn't as easy as, I will write this code and then the CPU will itself parallelize. No. If you want to write the optimal version of this in Java, in Golang, in Rust, you will have to write it somewhere like this. I need to find the sum from 1 to 1 million. I will split this into a bunch of 10 chunks, let's say. 1 to whatever this is, 10 to the power 8, and then 10 to the power 8 to 2 into 10 to the power 8, and then 2 into 10 to the power 8 to 3 into 10 to the power 8, so on and so forth. You will create a bunch of chunks. This is the first 10% of the sum that I need to find. This is the next 10% of the sum that I need to find. This is the next 10%. And you will write code that looks something like this. For slice in, slices, let's say we store these in like a bunch of slices. You will do a thread.spawn, some function over here, which will actually find the sum for that. Run a for loop to find the sum. And then eventually you will aggregate the results from all 10 of the cores and be like return, answer 1 plus answer 2 plus so on and so forth. So it's slightly difficult to write multi-threaded code. You can't just assume I write a for loop in Golang and it will be extremely fast. It will run on multiple threads. No, you have to write code as an app. As a developer, it's your responsibility to, write this code to spawn threads, to tell the compiler of Golang, of Rust, please break this job down into 10 parts and individually do these on 10 different threads and eventually accumulate them into a answer variable. How would you do a daily task? Let's say if you have to do 3 things today, if you have to, eat breakfast, get some medicine and go to the beach, maybe not go to get medicine and get food. You can either do all 3 of these together yourself. So sequentially, I will do 1, then 2, then 3, or you can parallelize. I will do one thing, you do the other thing, you do the other thing. And when the results are there, I will just join the results and all 3 of my tasks are done parallelly. That is what this code on the right would let you do in a language like Rust, Java, Golang. So the question is, Harkirat, there is no point of vertically scaling a Node.js process. You are saying, it works for these guys. And for these guys also, it only works if you write code like this. I can't write a for loop and assume it will run on multiple cores. I have to tell the compiler, hey, please spawn a new thread that does this, spawn a new thread that does this. And here I will, of course, find the sum from, for the first iteration, I'll find the sum from 0 to 10 raised to the power 8. For the second iteration, I'll find the sum from 10 raised to the power 8 to 2 into 10 raised to the power 8. But they're happening on separate threads. They're happening on separate cores. They are parallelly doing the results, and then you're accumulating it eventually. Can we see this in action, Harkirat? Can you show me, okay, this, whatever you're saying actually happens? Sure. Let's create an infinite while loop. And let's try to run this locally on, whatever machine you might have. You might have to install htop if you want to see stats like these, like I see on my machine. You can also run top and you'll see some, but either way, you need some way to monitor. Or you can also open, if you're on a Windows machine, which I've seen a lot of people are, you can open your system analyzer and look at the CPU usage. Either way, let's try to create not just a for loop that finds the sum for a very big number. Let's create an infinite for loop. Keep on running forever and ever. Let's copy this code. Very simple. Let c equal to 0, initialize a variable, and then an infinite while loop that keeps on running the same thing again and again, never stops. This should keep the CPU very busy. Ideally, you would want if I am on a 10 core machine, this should parallelize. This heavy task of increasing C should be parallelized on various threads or various cores. But does that happen? Let's see. Let's copy this code. Let's open a random variable, a random folder. And since I don't need any dependencies, I'm just going to open it here, vindex.js, and paste it. You can open a file in Visual Studio Code, in Notepad, wherever, and paste it. I'll wait for 10-15 seconds in case you want to try it locally as well. What have I done? I've just created an index.js file where I've put the contents that were present here on the website, which is defining a variable and then running it in an infinite for loop. 10 more seconds and then I will proceed. I have used Vim, feel free to use Visual Studio Code and open the file and run it. Let me just open it in Visual. I actually cannot. You get the idea. It's fairly simple. Just open the file and then run the file. Node index.js. What is this doing? Infinitely running a for loop that's trying to compute something. Of course, it's computing a very useless thing, but it's trying to compute something. How many cores of my machine do you think are running? If all of my cores of my machine were doing this, the Zoom call would have stopped. The Zoom call would have at least fumbled a bit. Sorry, we have a very expensive operation. If I open GTA on a very own laptop of mine, then of course the laptop will begin to struggle a bit, right? I cannot open Zoom in that laptop. So if this was actually multi-threaded, you would have begun to see some interruptions in the Zoom call. If it is not happening, it means Zoom is running on a separate thread, most probably, or a separate core is able to handle all the Zoom load, separate one, the browser load, and then a separate one is running this one of them is very busy right now. One of these cores is running at 100% capacity, trying to, calculate the sum from 0 to infinity. But the rest of them are, doing this terminal, Zoom call, so on and so forth. Great question to ask at this point is, Harkirat, you are on a 10 core machine. Does that mean you can only have 10 applications running because each core will handle one application? Not exactly. If you've gone through a class on operating system, you can have multiple applications. They interleave between each other. Of course, if I start multiple applications that are infinitely running a for loop, then none of them will be idle at all, and they'll still keep interleaving, but the processes will become extremely slow. Versus when you have a browser, a terminal, a Zoom application, the CPU doesn't need to be working all the time. For example, right now I'm sending you video at 30 FPS, which means I have to send one chunk every few seconds, every few milliseconds. So I don't need infinitely running. I don't need 100% of this virtual CPU, this CPU's, compute. I might be like, bro, I'm going to send something to the other side, this video to the other side on Zoom to my friends once every 30 times in 1 second. So please send it once, and then, you are free for the next 300 milliseconds or 30 milliseconds. Then please send another frame, then free. So they can remain idle from time to time and they interleave. The same CPU might be first running my browser code, then might be running, this terminal code, then might be running Zoom, so on and so forth. But one of them is very busy right now. How can I confirm that? I can open another terminal where I can run htop, which lets me see the stats on my machine. And what does it say at the very top? What is the most computationally expensive process running on my machine right now? It's this one at the top, which is node index.js. What's the second most computationally expensive? It's OBS, that's recording the video right now. What's the third most computationally expensive? It's Zoom app, that's sending the video. And everything else is like 8%, 2%, so on and so forth. But 99.3%, which means completely using the powers of one of the cores. What is that process? That is the infinitely running for loop. That makes sense as well, right? If you have an infinitely running for loop, and if you're on a machine, CPU is not like an employee who has labor laws. CPU can run at 100% capacity forever. So if you have an infinitely running for loop, then of course it will run forever. Harkirat, why is it less for OBS and Zoom? Because Zoom might not need to, as I said, send everything at every point. At some point it might become free from time to time, which is why it's not able to use 100%, or it doesn't need 100% of any CPU. Harkirat, what if I start 100 applications? Then what will happen? What you would expect? They will begin to chop out. Why? Because even though this for loop should ideally keep running, the OS will not have the time to pick it up from time to time and run it, and hence it will slow down. That's what happens when you open GT on a very old laptop, right? Hopefully this is clear. One CPU is being used by this guy. Now the question you might have is, Harkirat, to fir Node.js is extremely powerless language. You should never use it. It only runs on a single thread or a single core, and you are on such a big Mac machine, yet you're not able to use it to complete power. Sort of true, but you can do a bunch of things. You can do this. I have to do something computationally expensive. Let me start multiple Node.js processes. Let me start 3 Node.js processes so that I'm able to use 3 CPUs. Of course, it becomes very hard to share data between them. They can't really talk to each other, which is something you can do in a language like Golang or Rust. But you can be like, it's fine. At least the infinite for loop is running in 3 places. So I have 3 workers that are doing work. I was able to parallelize Node.js. My Node.js runs on multiple threads or multiple vCPUs. My Node.js is multi-threaded. Can you say that? You can technically say that. You can if you're on a big machine, you can run multiple Node.js processes in various terminals. And what would that do? If you look at desktop now, you will see the top 3 processes are node index.js, all of them running 100%, 100%, 100%. So can you make a Node.js process use all the power of your machine? Yes. Then why do I need Golang, Harkirat? As I said, number 1, this is very ugly. Opening 3 terminals, doing this. It would be nice if I run a single command that's able to parallelize. Number 2, it's very hard to share data between them. If this thread wants to send some data, this thread becomes very hard. That becomes much easier in languages like C++. That becomes much safer in languages like Rust, which is one of the reasons that Rust was introduced. Rust needs to be extremely memory safe when it comes to cases like these. If you're spawning 2 threads, they should be able to allow to share data between each other, like amongst each other, without having dangling pointers or things like these. So we have found a weird way to make Node.js sort of work on a beefy machine and extract all of its power. But let's see how the same thing happens in Rust. If you were supposed to do the same thing in Rust, would you run 3 different Rust processes, or can you do something better over there? If you don't understand this code, it's fine. This is, syntax is a little different. We're using something called the thread. Think of it as pseudocode all along. I've defined a main function. I'm iterating from 0 to 1 to 2. So I'm running 3 iterations of this. And rather than doing, a for loop over here infinitely, I'm first spawning a thread inside which I'm creating a counter and then running a for loop. I'm not running the for loop directly outside over here. I'm first spawning a thread, and then in that thread, I'm sort of running the for loop. And then I have another for loop in the main function call. So when I start this function main, when I call this function main, when I do the Rust start, let's say, what happens? Control reaches here. 3 threads get spawned. 0.3 means it will run 3 times. 0 for I equal to 0, I equal to 1, I equal to 2, or underscore equal to 0, 1, 2. And it will spawn 3 threads, which are also overworking. They are running an infinite for loop. And then the main function will also run an infinite for loop. So we ideally have 4 processes running, or 4 threads running. 3 of them trying to, find some sum. This one just ideally running and, not doing anything at all. And if you don't understand this code, it's fine. I hope you theoretically understand it. You're spawning a thread, which means, this is the thing that Harkirat said Golang provides you, or Java provides you, or Rust provides you. It lets you spawn threads where you can, tell another person, okay, please do this job, or tell another vCPU, okay, this can be run on a different machine, a different CPU, this can be run on a different CPU. That's exactly what we're doing here. If I try to run this, and it's fine if you're not able to run this if you don't have the Rust compiler locally right now. I'm just pasting this in a file called main.rs. Will this work without a cargo? It won't. I'll have to do it in. Okay, let me initialize an empty Rust project. mkdir week 22. So if you have cargo locally, which means, you know, the package manager of Rust, very similar to npm. How do you initialize a empty package.json? You run npm init -y. Similarly, how do you bootstrap a Rust application which has the equivalent of package.json, which is cargo.toml here, the equivalent of index.js, which is, you know, whatever main.rs here. You run cargo init. When I run cargo init, it initializes a Rust project for me. If I look at the files, it has a cargo.toml file, which is similar to package.json. It also has a source folder, which has the main.rs file, where I can just replace the contents of this to be the code that we have. Cool. So I've just initialized the Rust project. How did I do that? Cargo init inside the folder where I want to initialize it. And what is the second thing I did? I've restarted, I've replaced the contents of main.rs. Now I can run this Rust project locally by typing cargo run. Gives a bunch of warnings, that's fine, and then remains stuck over here. Notice what happens here. What does this say? It says, yeah, there is a process using 385%. What does 385% mean? It means 4 vCPUs. It's using 4 vCPUs or 4 CPUs. And what is the process? It is this cargo run process that's sort of running Rust on my machine. What does this tell you? I did not have to open 4 terminals. In a single terminal, in a single Rust file, I told, okay, bro, you run an infinite for loop and also spawn 3 threads that do the same thing, that run an infinite for loop. Of course, in the real world, you're not running infinite for loops. You'll be like, it's a handle a request that's coming from a user, an HTTP request, or, you know, as I mentioned, a use case of, you know, finding the sum from 1 to 100 billion. Then you'll be like, the first thread, please find the sum from 1 to 100 million. Second thread, please find the sum from 100 million to 200 million. You'll get all of these values and then finally add them up and return them over here. You'll parallelize this. That will be a real world use case, but hopefully it's clear that a language like Rust, or even as I said, Golang, where you can create subroutines, and Java, where you have a thread pool that lets you create threads, does the same thing. You can have something using more than, you know, 1 CPU of your machine, which is good. Which is great for, you know, a backend application, because you want to scale backends as much as you can vertically. If vertically doesn't work, you do scale horizontally as well. But, you know, for the first 100,000 users, scaling vertically is great. And it's much harder to vertically scale in Node.js. Can you do it though? You can. This should say vertical over here. Implementing vertical, not horizontal, vertical scaling in Node.js. Let's say, I say कि नहीं यार फिर भी you have to implement vertical scaling in a Node.js process. Somehow figure it out. Firstly, let's do a poll. Do we understand everything I've taught until now? Oh. Let's take some questions really quickly then. 82%. I think 2 or 3 questions or a recap will be fine. So, you know, small 3-4 minute break. So now is that question answered? Okay, even though JavaScript is single threaded, how does it run asynchronous operations? This question sort of is a great question to ask to check someone's fundamentals. Okay, you know, do they fundamentally understand JavaScript or not? Great. Cool. Shall we proceed? Can we move on to, you know, the cluster module? Are we good to go, guys? Or do we need more recapping? I'm assuming so. Are we good to go? All right. Not taking a break. We can take one later on. 87% is great. Let's proceed. Implementing horizontal scaling in a Node.js project. Let's say you do want to implement horizontal scaling. If you're like, I have to have a very beefy machine. I want my million users to go to this single beefy machine, and I want to use Node.js only. What can I do? You can either start multiple node projects, and you'll be like, okay, I will just start node index.js 10 times. And then, you know, my machine is running 10 different Node.js processes, and hence I have used all the powers of my machine. But this has a lot of problems. First, this is a very ugly approach. Slightly better approach is just spawning multiple requests on a worker thread that someone suggested. Number two, processes will have port conflicts. The biggest issue here is, if you start multiple processes together, if this is an Express server running on 3000, you cannot start another Express server running on port 3000. You cannot be doing this. There'll be a port conflict. If you want to try it out quickly, try it out. You might have already seen this from time to time, but let's see if I have a Rust Express project somewhere here. Let's just do it on a next step. Cannot do it here. Which of these is an Express project? Week 14 isn't. Oh God. Let me quickly create an Express project, even though I'm assuming this is pretty straightforward. We'll say cd Express project. Import Express from Express, const app equal to Express, and then app.listen 3000. If you write code like this, of course there'll be a bunch of handlers here, but assume there are no handlers, and run node index.js once, it will tell you don't have Express. You also don't have package.json. So npm init-y, npm install Express. I'm not using TypeScript. I'm simply using JavaScript. Let me open this in Visual Studio Code so it's easier to look at and understand what's happening here. If I run node index.js over here, still gives you an error. Okay, you cannot import like this because this is a JavaScript project. Equal to require. There you go. You have this, Express project, let's say. Cool. If you run this once, it's all good. You have a single thing running on port 3000. If I go to Google Chrome over here and go to localhost 3000, it says message hello world. But if I try to run the same thing in another terminal, I repeat, I open another terminal and run node index.js, what happens? A port conflict happens. It says address is already in use. You cannot start another process that's running on the same port. So the naive approach that we were talking about, Harkirat, we will do this, we will start multiple node index.js, does not work. So what can we do? We can use the cluster module. This might have changed recently, by the way. Someone mentioned worker threads, so maybe they are a better way to do this. But historically, cluster module is something I've used, and that also has recently changed its API. So today, when I was doing this, I realized cluster.isPrimary is depreciated, and there's another way to start multiple or spawn multiple processes using the cluster module. So feel free to Google a little bit also after the class to figure out is there a better way to do this today. But this was conventionally the way to scale Node.js applications for the longest time, probably is today as well. What does it say? It says import Express from Express. Firstly, we'll do whatever we were doing in importing Express like we were until now. Import cluster from cluster. This cluster is something that Node.js provides you, which means it's a Node.js internal library. You don't have to do npm install cluster. It comes pre-built with Node.js, very similar to FS or HTTP. All of these come pre-built with Node.js. You don't have to externally install them. Import OS from OS. This library we are only using to find the total CPUs that exist on this machine. Const total CPUs equal to os.cpus.length. This will give you, in my machine, this will print 10 because I have 10 CPUs on my machine. Const port equal to 3000, nothing too complicated here. Now comes the mildly complicated bit. If you've done, forking in the past, then this will be straightforward. If you haven't done forking in C++ in the past, then this might seem a little overwhelming, but bear with me. What are we doing eventually? We are starting multiple processes somehow. Which means this file that you see here will run multiple times. It might run 10 times or 20 times. Which means the same code is going to run for all of these workers, right? Yes, Harkirat, the same code will run. So what this if check over here does is, is this the user started process? Eventually, I will start a process by running node index.js. And this process needs to start a bunch of other processes, right? I will start a process by running node.index.js, which we want, it spawns 10 different processes that handle all the incoming requests. So what does the cluster module say? It says here, if this is the primary Node.js execution, which means if this is the Node.js index.js process that's running by the user, then run this code. And what does this code do? It says, for let I equal to 0, I less than total CPUs, I++, cluster.fork. What does this cluster.fork do? It starts another process that pretty much runs the same thing, which basically means that process will also start from the top and try to run all of this. But for that process, cluster.is primary would be false, which means the control would reach over here. And here you can write all of your express logic to do whatever you're supposed to do. And if you are using the cluster module, there will be no port conflicts. Even though you might feel like, Harkirat, we are still starting 10 processes, there should be a port conflict. There will not be another port conflict if you are using the cluster module to fork the same process rather than starting Node.js process again and again in a terminal. The biggest thing that will feel overwhelming over here is this cluster.is primary path. What it basically means is, okay, you will run node.index.js once in your terminal. And once you do, the cluster.is primary variable will be true over here, because this is the primary execution of this index.ts file. This index.ts file is running from the top. And this is true because this is the user started node.index.js. But this ends up forking 10 times, which means this ends up starting another 10 processes. It ends up starting node.index.js, let's say 10 times. But for all 10 of these, cluster.is primary is false. For this guy, it was true. For all 10 of these, again, the code will start executing from the top, but the control will reach the else statement where you define your express logic that actually handles the request. What is the express logic? Const app equal to express. It also prints on the screen worker process.pid started. What does this tell you? Every process will have a separate PID, which means these aren't lightweight threads that you're starting. You're starting multiple processes. This is starkly different to how you do it in Golang, where when a request comes, you spawn a subroutine. Okay, yeah, you handle this request, you handle this request. Here, we just start 10 processes. They are actually separate processes. Only it's just cleaner for us to write, and there is no port conflict. A single node index.js is able to start 10 processes, all of them listening on the same 3000 port over here. A simple route, hello world route. A slightly better route, app.get/API/:n, which means if you want to find the sum from 1 to some number n, this request handler will do it. If you look at the code, that's exactly what it does. It gets n from the parameters, starts count equal to 0, let count equal to 0. If n is greater than a very big number, then we pad it to a small number, and then we iterate from 0 to that number and increase the value of count, and then finally return that to the user along with process.pid. We want to eventually debug, okay, are multiple requests being handled by different processes, which is why we also send back process.pid here. What is process.pid? Whenever you start a process on your machine, it has an associated process ID, PID. If you start a node index.js, if you do a go run some Golang file, every process that you start, even my Google Chrome browser that I have here, has a PID, process ID associated with it. And this log over here should confirm, okay, we are able to start multiple processes. Let's try to run this code and maybe see we understand something better with the code. Pasting the code here again to quickly go over it from top to bottom. Bunch of imports. You can also hardcode this. If you don't want to use OS, feels overwhelming, hardcode this. If you have 5 CPUs on your machine, hardcode this to 10 or 5. If cluster is primary, we put a bunch of logs and then we fork the process 10 times. We also say, okay, if one of these workers exit, please fork again, so that if it does, one of the workers do end up crashing for whatever reason, we restart it again, so that we still are using 10 CPUs on our machine. So if any of them stops, you do this. You can also be like, I will exit the parent process, which will exit every other child process as well. When this happens, a lot of times this is the approach. If one of the worker dies, we kill everything. And then, PM2 will restart the application again. And, that's how the restart happens. Or you can just be like, yeah, if one of the workers stop, I will just do a cluster.fork to again restart it. What does cluster.fork do? It restarts this file again. It starts a new process with the same file. But this time, cluster.isPrimary is false. And the control reaches here and you start an express server that is listening on port, whatever was the port over here, 3000. Let's run node index.js. We cannot because we have these kinds of imports. Let's convert this into a TypeScript project. Try this later on. Let me just, quickly do this. And, you feel free to try it in your own time. You can also try it right now. But again, it'll take some time for you to, I guess not, like npx tsc --init. That's all I did to initialize a tsconfig.json. And then I'm going to replace index.js with index.ts because this is TypeScript code. Then let me do npm install express. Why does cluster there we go. npm install express, npm install at type/express. Notice I did not have to do an npm install cluster. And then this is the code. If I compile this, how do I compile this? tsc-b, it will create an index.js file. It is creating it in the root folder because I did not update tsconfig to have a root dir and an out dir, which is something that we usually do. But today I did not do it because we have a single index.ts file. This is the TypeScript file. I ran tsc-b to convert it into a JavaScript file. Let me run node index.js. And it keeps on erroring because I have something already running on port 3000. So let me stop and let me restart. And notice what it says. What does it say? Worker, this thing started. Worker, this thing started. There are multiple processes that I have running with different PIDs, which means they are different processes. They aren't lightweight threads. They are different processes that are now handling requests on port 3000. If I go to localhost:3000/API/10 or 1000, what does it say? It says final count is 500500 and a process.pid, which is 91296. There is one small problem in this. What would you expect when I refresh this page? You would expect the PID keeps changing, but notice the PID remains the same. It did change initially, but now if I'm refreshing, it remains the same. It will remain the same for a while, and then eventually if I refresh again, you'll see it will change. Which means even though we have multiple processes, the same one is handling all the requests here. Does anyone know why? Because the answer is I don't know why. Statefulness is what I thought as well. Maybe caching, same API, caching where? Just single threaded, that's the wrong answer. Do worker threads run on far left core of the CPU? I don't understand that question. It checks for parent process, for child process, copying the parent one. Yes, exactly. Cool. I guess no one knows the answer. I am assuming it's somehow, the request when it goes out from the browser, it has some sort of a fingerprint. As you can see now it changed, but it has some sort of a fingerprint, and then the backend is like, nature, I will return it from here as well. This does not happen if I start another browser. If I start a Brave browser, it is handled by 91288. Here it's handled by 91292. If I send the same request via curl, you will see 91291. So it does happen it is multi-threaded. Firstly, I thought this isn't working only. When I was testing this out before the class, I was like, I'm refreshing. Why is this not changing? Then I realized it's probably, something is up with how the backend handles requests from the same device. And, just pipes it to the same core for some reason. I don't know what the reason for that is. But, if you wait for a while, then you will see the PID change. For example, if you wait for like 10 seconds, then it changes. But if you keep refreshing with no gap of 10 seconds, you will notice the request goes to the same PID. I don't know why. Probably something on the backend. Cool. That's pretty much it. That's how you do, vertical scaling in Node.js. And try to figure out the stickiness thingy. I have no idea why this happens. Why it gets routed to the same PID. Capacity estimation. All right. So I don't know. It could be a break time. We could take a small break. How's it going? Should we take a break, guys? Yes or no? I can answer some questions during that time. I don't think we'll be able to reach indexing today because we have to do some backend stuff. Should we take a break? And that is a yes. So we will take a break. We will restart in 9 minutes. So at 7:15, I would assume that would be in India time. Tasks that can be offloaded to other things that have to wait, but can wait asynchronously is what you should use Node.js for. Because, if they're being waited on asynchronously, the Node.js thread can do other things. Diagram. Okay. Cool, guys. Let's get right into vertical scaling. So slide number 4. Before that, capacity estimation. This is one of the weirdest, things we have to sort of check off our things to do. I have a video with 𝗟𝗶𝗹𝗀𝗀𝗀 where we did, YouTube, and the first thing she asked me was, how much video do you think is being uploaded every day on YouTube? So these are the questions that, are asked in these sort of system design interviews a lot of times. This is what capacity estimation means. There are some practical learnings from this, but a lot of this sounds pretty useless to me too, as an interview question. I don't know how much videos uploaded to YouTube every day. I don't follow those stats, right? But a lot of times you are expected to, arrive at a number close to what is that the load of a system like this. What is the expected load? So you'll sort of face these questions from time to time. If you're building a YouTube, how much do you think every users come? How many users do you come every day? How many uploads do you happen every day? How many uploads do you think happen every second? So on and so forth. So practically they become useful if you want to understand how to scale your system. We'll understand a few architectures here: Paytm application, chess application. I'll also introduce a third one. If I forget, remind me. A video transcoder application. This is a common system design interview question where they'll ask you, how would you scale your servers? System design mein, they will never ask you, okay, your system has 10 people, how would you build it? They will ask you, your system has 1 million users, how would you scale it? How would you handle spikes? What are spikes? You had only 10 users and suddenly you have 1 million users. And then you have 10 users again. How would you scale up your infrastructure? How would you scale down your infrastructure? How can you support a certain SLA given some traffic? What is SLA? SLA stands for service level agreement. SLA is basically mean, if you ever use AWS, let's say, or if you use Razorpay, they will give you an SLA, service level agreement. They will say, okay, 99.9% we will be up, which means, in a year we might go down for whatever that is, 30 minutes, but 99.9% uptime is our SLA. And if we go down below that, you don't have to pay us, or you have to pay us 20% less. You get a discount in case we don't follow our SLA, in case we do not do what we promised you. So that is what an SLA is. And the question here is, the statement is, how do you support a certain SLA given some traffic? Now let's say Razorpay said, okay, you don't have to pay us anything if we don't follow the 99.9% uptime. But if you make such a promise, how can you make sure you always do follow that SLA and never can you go down for more than 30 minutes? These are the questions that are asked. Answers usually require a bunch of, number one, paper math. If the SLA is 99.9% and the maximum spike that is expected is 1 million users, then I should always have some servers running, or I should always every 3 minutes check, should I scale up, so that if there is a spike that happens during cricket matches, and cricket matches happen 2 times a year, then during those 2 times my infrastructure will wait for 3 minutes before it scales up by a lot. So these are the things that you have to think of. What did I say again? I said, in capacity estimation, you have to put things like these. IPL happens twice every year. My SLA is 99.9%, which means my downtime can be at max 30 minutes in a year, which means whenever this spike happens, I have to recover at max in 15 minutes. If I don't recover in 15 minutes, then, I've failed to follow through on my SLA, which means whatever is the logic of mine that auto scales servers, that brings up a lot of infrastructure, needs to keep checking probably every 5 minutes. Is there a spike? Do I need to auto scale? Whenever a spike happens, a spike like IPL happens, what you do is you go to a bunch of providers. The IPL bandwidth that is expected to be handled in India, whenever people are watching, 20 crore people are watching the same thing, is it cannot be handled by a single cloud provider. Only AWS does not have enough wires in India to handle that kind of bandwidth. So you have to have multiple vendors available. And whenever the spike happens, how can I in 15 minutes quickly start those vendors? So these are the things that you talk about when you do capacity estimation. Estimating requests per second. There is some obsession that in these interviews with the per second requests per second bandwidth. So if you will say, they'll ask you how many requests do you think come in a day. You will say, oh, there are like whatever, a million requests or a million users that will come in a day, or a million active users. So they'll ask, oh, how many requests will each user send? You will say maybe 10 requests. So they'll say, so there's 10 million requests in a day. What does that translate to seconds? So, you have to do whatever 10 million divided by, whatever the number of hours are in a day, so on and so forth. So 10 million divided by 3600 into 24, I would assume something like this. These are the number of requests that I need to support per second, right? If there are 10 million requests a day, that means there are 10 million divided by 3624 into 24 requests a second. When you arrive at this number, the requests a second number, let's say that number is, whatever, 100 requests a second. Then you have to be like, Acha, how much can infrastructure in how much can my infrastructure support? If I have a single Node.js machine in AWS, how much can it reasonably handle in 1 second? Let's say the answer is 10. It's not 10 for Node.js, but let's say the answer is 10 requests a second is what your Node.js process can handle, which tells you what? I need to have 10 machines available because I need to handle 100 requests a second. So that is how you will arrive at the first number. For an application like this, assuming my Node.js process, you of course need a realistic number here. A Node.js process can handle 1,000 requests a second, and let's say the number of requests that you're receiving are 10,000 requests a second. So you need 10 servers available that can handle all of this load. Then they will ask, what happens if there is a spike? How do you scale up, scale down? So assuming you have monitoring that tells you how many requests are coming, and you can somehow spit out the current number of requests per second in the last 10 minutes was this number. You can sort of use this to scale up or scale down your infrastructure. Auto scaling machines based on the load that is estimated from time to time. From time to time, you need to check what is the current load on these 10 machines. And if this load becomes a lot, then you have to scale up. If this load becomes really less, then you have to scale down. So the final architecture will look something like this. Let's say you have 4 machines right now in AWS. All 4 of these are receiving requests from user, and every few minutes they need to somehow aggregate. In the last 10 minutes, I received 100,000 requests, a million requests, a million requests, a million requests. This somehow reaches a system. How it reaches a system, there are multiple ways. You don't have to synchronously do this. You don't have to be like, HTTP request came. Let me send an HTTP request to tell the other side, a request has come. No, you aggregate them. Whenever 1,000 requests come, I will let the aggregated service know 1,000 requests came. Even if this gets missed, it's fine. So that is how you will somehow aggregate. In the last 10 minutes, these many requests came. You will spit this number out to some database or some process, which will be like, oh, the number went up. It will tell the auto scaling group, you need to scale up. You need to bring up 10 more servers. The load in the last 10 minutes has increased by a lot. Similarly, if this load decreases by a lot and this final number becomes 10 requests a second, then this process, whatever this process is that is scaling up and scaling down, this can be different things based on how crudely you implement this. It can be a Node.js process for all practical purposes. I will receive every 10 minutes the current number of requests, and I will scale up and scale down my infrastructure based on that. Do we understand the diagram? When we reach auto scaling groups tomorrow, maybe we'll actually implement this as well. But do we understand, at least theoretically, multiple machines sending data to a single service, which is aggregating the total number of requests per second, and then, sending it to a process that's scaling up or scaling down? We don't understand this. 80% understand this. So there is some obvious question that I've missed. Can you post it in Q&A really quickly? How many requests can Node.js handle? It depends, right? Depends on how heavy that request is. If this request is simply returning back the user hello, then not a lot of them, maybe 20,000 requests a second. If that process is doing some for loop over 1 to a million, then of course it can handle lesser. There is no port conflict, you said, so means one port is handling all 10 requests. Yes, that is exactly the pro that cluster module provides you. Someone said an answer for cluster PID. Recap. Please come once again. Okay, let me explain one more time. You are an engineer. Forget that this is a system design interview. You are actually an engineer, and you created a simple website to begin with. Eventually we'll get into complicated use cases like a real-time game and a video transcoder. But for now, you created a e-commerce website. All right. Now, right now you have a single server over here on your e-commerce website, and it's receiving requests from end users. This is the backend of your e-commerce website. Where is it running? It's running on a EC2 machine, let's say. Users are sending requests here. Let's say suddenly 10 million users come. Some sale happens, everyone's visiting your website, and you have no systems to scale up or scale down. Then what will happen? Your server will begin to get choked. Your users will not be able to receive requests. They will get a bunch of timeouts. They'll just get bad status codes, or they will have to wait for a really long time for a response to come back. And hence, this is bad. You should scale up your infrastructure whenever this happens. The question is, how do you know how many requests are coming? And how can you, based on that, scale up or scale down? One crude way to do this is, not crude, this is actually pretty good. For an application like this, what makes sense is you can create an auto scaling group, which use as a buzzword for now. Tomorrow we'll understand this better. What does an auto scaling group mean? But from first principles, what does auto scaling group means? You give it a number, start 10 machines, and it starts the 10 machines for you. You give it a number, now scale down to 3, and it scales down to 3 machines. It terminates the 7 machines. So the most crude way of doing this is, create an auto scaling group and tell it, bro, your average CPU usage should be 50%, let's say, which means you tell the auto scaling group, if your CPU usage is going above 50%, if it becomes 80%, then please scale up the infrastructure. Please increase the number of machines that currently exist so that this number goes down to 50%. What is the other thing you're telling it? If it ever drops to 10%, let's say all the users leave, it is night time in India right now, then of course no one is visiting your 4 servers. So the average CPU utilization will go down. And then what will the auto scaling group do? It will be like, average should be 50%. I will delete these slowly so that the average, goes up to whatever, 30%. And of course, you always need one machine. You cannot be like, 30 is less than 50, so I will delete the last machine as well. The auto scaling group will of course have a minimum, but you get the idea. That is the most crude way to do auto scaling. But when you are asked this question in a system design interview, they will give you weird use cases. For example, one use case was this, the metric is on requests per second. They will give you, this single process can handle 10 requests a second. And they will say, how will you build a system that scales up and scales down based on the number of requests? So your answer should be, or your implementation also should be, I will have a certain number of machines, and these machines will every 5 minutes tell another, let's say, Node.js process for now, I received 100 requests in the last 1 minute or last 10 minutes. I received 1000, I received 2000, I received 3000. This will create an average. On average, we have received, let's say, 100 requests a second, and it will tell this to another process, or even you don't even need another process. This process itself will tell the AWS auto scaling group, scale up. The number of requests per second that we're handling is very high, so please scale up. And if vice versa, if the number of requests that we're handling on average goes below a certain threshold, then we can scale down as well, because we are over provisioned. Then we have too many machines, and we can get rid of them to save some costs. So this is one architecture to do auto scaling. When you have constraints like we have a very strict SLA, and the number of requests per second that our process can handle is X, and you need to scale up and scale down whenever this spike comes, whenever the load might increase slowly, there might be a spike as well. So irrespective of what happens, you need to scale up or scale down your infrastructure. This is the slightly more over-engineered way. This is the most crude and easy way. Give it an average CPU utilization, give it an average incoming bandwidth. If the incoming bandwidth goes above a certain threshold, then also scale up. If it goes below, then scale down. Do we now understand this crude way of doing capacity estimation and scaling your systems? This is exactly what we'll try to implement tomorrow. 50% kind of a thing. All right. I think that was good only. Yeah, 90%. Great. Cool. So now comes a slightly more complicated. What if they ask you, now you have a real-time application. You have a chess-like application. How would you scale now? And in a chess-like application, you don't have requests per second. You have persistent connections. If there are 100,000 people active on your website, they aren't sending you a lot of messages. The number of messages they're sending is low, but they have a persistent connection to your servers. And persistent connections are expensive. You can only have 10,000 persistent connections. There's some metric like this. Okay, for a Node.js process, if you have more than 10,000 sockets open, you'll run into issues. Which means for this real-time application, the metric that you're worried about is not the number of requests, but the number of people currently active on the website. If I go to chess.com, you will see they have this number aggregated somehow. Okay, currently these many people are playing. If you go to a bunch of other live streaming websites like Twitch, they a lot of times have on the top right, okay, currently 8,000 people are active on this website. So you always have this number. How this gets aggregated is a different question. In a distributed system like this is also a challenge. Okay, this machine has 100 connections currently open. This has 1,000 connections. This has 1,300. This has 1,400. How do you aggregate this? And, the answer remains the same. You create a aggregation service like this. Anytime a person connects, this guy tells, hey, I have 1,000 people now. Every time a person disconnects, this guy tells, sorry, I have 999 people now. You can also back this off. You don't have to, not every change needs to go from here to here. Even if this number is off by a bit, or is slower to finally catch up to the real value, it is fine. You don't need this number to be exactly accurate at all times. So every 2 minutes, they can keep reporting their active users. That number will reach here. And this will send this to the database so that users can see this on the front end as well. You want this aggregated number shown on the front end as well. This will also try to find an average. Okay, 88,000 people are live. We have 4 servers currently, which means every server has 20,000 open sockets. I need to increase the number of servers because I know, okay, our single machine can only handle 10,000 at a time. So this will tell an auto scaling group, it will tell AWS, please scale up to 8 servers, and it will, the number will get increased. If these connections go down, then of course, vice versa would happen. Another, one very challenging thing that happens here compared to the last use cases, if you had 20,000 people here and you scaled up, you need to slowly drain these users to the other server. You need to move some of these users to the other server, which, requires a bunch of client side logic, which means on your website code, your React code, you write this logic to, disconnect and reconnect to a fresh WebSocket server. The other problem comes when you drain down. Let's say, abhi to we increase the number of servers. What if you decrease the number of servers? Then, this server will die. All the people that had persistent connections here now need to be moved to other servers. So this is one thing that becomes challenging if you have WebSocket connections. This is not a challenge for HTTP servers. For HTTP servers, requests go, request finishes. So if a server dies, it's fine. All the requests will start to get route to the other server. But for a WebSocket connection, the server that is dying will take down all of these WebSocket connections with it. So you have to reinitiate those connections to a different server from the browser. You probably need to show the user somewhere on the UI, you are disconnected. And then, eventually when they reconnect to a server, show them you are reconnected, something like that. But yeah, that's a brief of how you do this in a WebSocket system, a real-time chat application. Do we understand this? Hmm. 82%. Let me share the last one and then let's call it and do questions. So that means we will do horizontal scaling tomorrow, which is fine. Yeah. The last one was a video transcoder. Then I'll open it to questions. The third weird use case is, video transcoder or Replit like website. Or you can say even lead code, but not really. Lead code submissions happen in 2 seconds. Replit pay, you have to give the user access to some compute for, sometimes 2 hours. And video transcoding also takes sometimes 2 hours. What are these 3 use cases? Let me quickly share. And then, the way you scale in all 3 of these is actually fairly similar. Video transcoding means when you go to youtube.com and upload a video ever, I don't know if you've tried it, but when you upload a video, you only give YouTube a single MP4 file. You give YouTube a single MP4 file and YouTube converts it into various qualities. It converts it into 720p, 360p, so on and so forth. 3 qualities. This process is called video transcoding. It is transcoding your 1080p file into various qualities. This can take a long time. This is a very expensive operation. What do I mean by expensive? I mean, converting a 1080p file to 3 variants will take a lot of the CPU on the machine that they're running on. So, if suddenly 100 people come to your website and upload videos, even though 100 as a number is really small, only 100 people are uploading, you need a lot of compute for this. You need almost 100, decently sized machines, because it takes a lot of, time for this to happen, for, an MP4 file to get converted to 360p, so on and so forth. So the question is, how do you scale a system like this, where, okay, you will have a use case where you have to have some compute ready for the user for a long time, because video transcoding takes 2 hours. And if you go to Replit ever and try to create a new REPL in any language, let's say Node.js, then also you have access to basically a Replit machine. I have a video on Replit, so you can look at it. I don't follow this architecture there. I follow a very over-engineered Kubernetes architecture. I do share this architecture there though. Okay, this is taking a long time for me. So when you go to Replit also, then you have access to a machine, because you have a terminal where you run a bunch of commands. They're running on someone else's machine. Same happens on LeetCode. When you submit, runs on someone else's machine. Only on LeetCode it's like very small. So this architecture isn't really valid for LeetCode. But for the other two, what you have to do is, whenever people come to your website and say, I have uploaded a video or I want to create a REPL, you need to give them access to some compute immediately. What do I mean when I say compute? I mean, you have to give them access to some 2 GB and, whatever, 2 CPU machine. This is exclusively for you for the next 2 hours. When you're doing an MP4 transcoding, it's a very expensive operation for a really long time. Converting 1080p to 360, converting 1080p to 720 is a 2-hour long process that needs access to both the CPUs at 100% peak. So whenever a user is uploading, they need access to some part of your compute. If this is all of the machines that you have in a very big pool, let's say, then you have to sort of share these machines somehow with users. Okay, if the first person comes, you give them access to the first machine. Second user comes, you give them access to the second machine. Third user comes, you give them access to the third machine. Then the fourth user comes, is when the question comes, what happens? Should we auto scale or should we do something else? And there can be multiple answers here. One answer is yes, please auto scale. So what you can do is, okay, whenever a new request comes to create a new MP4 file, or upload a new MP4 file, you can have a warm pool basically of servers. You can have a warm pool of servers. What does warm pool mean? It means they are ready. These machines are ready, but there's nothing running on them. They are ready to get a request from the YouTube uploader service. Someone uploaded an MP4, I will now handle it. And then, another person uploaded, I will now handle it. And as these handles keep on happening, you keep on increasing the warm pool as well. You always have, let's say, 20 machines ready that are warm. By warm, I mean, you get the idea, they're ready. They're not doing anything, but they're ready to pick up requests. If peak, you will only get 20 uploads in 1 minute. If at max your SLAs, if you send me 20 uploads, I will handle it. If you send me 21, I might not be able to handle it. But my SLA clearly states you can send 20 to me in a minute and I'll be able to handle it. So you probably need a warm pool of 20 at all times, so that as people send requests, you sort of warm pool keeps on increasing, and you keep assigning the machines one by one. Why do you have to assign every user a machine? Because as I said, this is a 2 CPU, 2 GB machine, that all those resources will be completely used for a video transcoding process. And the same is true for Replit. If you go to Replit, you get some vCPU, some GB memory, some space over there until your Replit session is closed. So they need to give you some part of their compute for a long time. So this is one way. What is the problem in this? Number one, you're maintaining a warm pool. You have 20 machines always running, which might remain idle. So you're playing for 20 machines always. Not a problem at scale. If you have a lot of machines, if you have 1,000 users, then it's fine. You pay for 20 extra machines when you're creating 1,000 machines every month. So the cost isn't anything compared to you paying. If you have throughout the month, you're starting 2,000 machines. Doesn't matter if you have 20 in a warm pool for a long time. It's fine. But that's the first problem. What is the second problem? Resource sharing is also sort of a problem here. You are restricting the user. You will only be you will have complete access to 2 CPUs, even if you are not using it. Maybe this 1080 to 1080 to 1080 takes 100% of the CPU, 1080 to 720 takes 100% of the CPU, but 1080 to 360p does not take a lot of the CPU. So, would be nice if this can be shared. If I can just have 20 CPUs, that can probably be shared by, 30 videos. Because, a lot of times one video reaches the 360p stage, so it does not need as much CPU. So you can't really share compute. You are restricting every video will have its own set of compute and GB requirements. So, that is the downside of this approach. But still a pretty decent approach to follow in, this third use case of having a Replit like website or a video transporter website, have a worm pool and increase the worm pool. What is the other thing you can do? The other thing you can do is an architecture we've discussed a few times. Anytime a video transport happens, you push it to a queue, and then, you have workers that asynchronously pick this up from a queue. And if this queue length becomes very big is when you scale up your servers. So, if 100 people submit a video upload, then you slowly can scale up. This length has become very big. Let me scale up the number of servers to 10. And then as this length goes down throughout the day, because they will transcode, and as they transcode, this queue will sort of become smaller and smaller, then you can scale down. So that is another sort of architecture. The problem with this architecture is it works for video upload, because video upload mein YouTube says, after you upload, YouTube says you please wait for 1 hour, video is processing. So, they have that kind of an expectation / SLA with you. This is not true for Replit. When you go to Replit, and that is why, Replit breaks if all of us will try to create Replit at the same time. They cannot have a warm pool of 1,000 people. They usually do not get a spike of 1,000 people. But, if all of us right now go here, then most probably will crash Replit because they don't have such a big warm pool. And they cannot use this queue-based architecture because this is slow. Queue mein you only have 3 workers, let's say, then everyone will pick them, slowly, one by one. Versus, and you can't expect that on Replit. Sorry, wait for the next 30 minutes, we will get computer for you. You cannot tell that to the user. Which is why this queue architecture will not work for Replit. What will work for Replit? The original warm pool architecture or a Kubernetes architecture that I've already discussed in a YouTube video. Let's call it here, guys. Boy, we discussed a little too much. I think I've been speaking for a long time. So let's, do some candid discussions, questions, all that jazz. Is there any other special kind of way to scale applications in some use case? No, these are the 3 I can think of. Generally, the thing that will be asked is this. I guess the fourth thing can be, cricket matches. Because when you have a cricket match, sorry, this is the last thing. Cricket match that's happening in Mumbai. Let's say this is the, India map. It's Mumbai. Then the video transcoding is actually something that doesn't need to scale. A single stream goes from the Mumbai server to some server, in some data center, let's say in Mumbai only. And this sort of converts the incoming stream, which usually is RTMP, over to, an HLS stream. The problem that comes is how do you send this to so many people? So usually the scaling problems we have discussed here is not about sending data. A lot of people will ask a lot of data at the same time. It's more about a lot of people will be like, give me some, I want to sign up, I want to sign in, I want to do something, or, very simple e-commerce website backend route handlers. This is a completely different problem. If you have a cricket match happening, the problem is too many people are asking for 720p video, which is a lot of bandwidth, and India cannot support this much bandwidth. So how do you 720p? A lot of people are asking for 720p video. How do you send this, for all practical purposes, MP4 video, or HLS is a better format that is used for streaming in these websites. How do you? This is the easy bit. Getting an RTMP stream, transcoding it to HLS is the easy bit, and creating 3 qualities out of it is the easy bit. The hard bit is sending it to so many people. How do you scale that? And the answer, surprisingly, over there is also auto scaling groups. In AWS only, there is a video on YouTube where Hotstar discusses this. How do they scale their infrastructure? The answer, surprisingly, was auto scaling groups in AWS. I thought they would have a very elegant / cloud native architecture, but apparently not. They use ASGs, which is something we'll be discussing tomorrow, to scale up infrastructure in case of spikes. All right. With that, let's answer some questions. It will stop all the processes. How can 2 different cloud providers come into picture? Oh, well, for example, in case of a cricket match, one cloud provider is not enough. So, you will have deals with multiple CDNs, content delivery networks, and, some of them will have servers in Rajasthan, some of them will have servers in Gujarat. And then, whenever the peak spike of IPL happens is when, you will turn on all cloud providers and be like, bro, everyone please serve the right traffic. If the crypto course launch, okay, answer that. Can you show the calculation for an SLA? Calculation for the SLA. For which SLA? For example, one basic paper math was the most basic paper math it was okay, our server can handle 100 requests per second, and our system has 1 million users. Each user sends 100 requests or 1,000 requests in a day. So I did what? I did number of users into number of requests in a day divided by 3600 into 24, which is the number of requests per second. That is the number of requests per second we have. A single server can handle 100. So how many servers do I need? This number, whatever this number is, divided by 100. These are the number of servers that I need to handle this. What's your second question? Sorry if I already answered this, but can chess game be made by HTTP server rather than WebSocket? For most practical purposes, yes. But there is one thing for which you cannot use HTTP. The thing with chess is you don't send a lot of data. So there are two benefits of WebSockets. One, whenever you're sending a lot of data, you should use WebSockets, so you don't have to do the 3-way handshake every time an HTTP request is sent. So that's one benefit. Chess you don't play a move as often, so it's fine. The other problem that there is always server-side events. You have to push events on the server. If one person makes a move, it needs to be pushed to the other side. HTTP cannot do that. You cannot push something via HTTP. So this guy either needs to keep polling, has the move been made, which is bad. Good thing is WebSocket. So you can make whatever you can make in WebSocket, you can make in HTTP by polling, but you shouldn't do that. Yeah, I want the mountain not to respond to my message. I will not. Please ping Ankur or Rookie. They will do it. End of month is here is when money gets spent. So should have it by 31st, maybe like 2nd, 3rd also. There are a lot of people like small, big mounties, but yeah, if it's less than $100, Aryan is the one who's clearing it. What are the best operating system? Open source blockchain, especially related to fintech. All DeFi protocols, Uniswap, Drift protocol have their contracts open source. Maybe not their code open source, but most of them have their contracts open source. You can look at them. All right, thank you. Notion doc is not open. Another Notion doc by Rohan Vaidya and one by 𝗥𝗲𝗬𝗀. So last two things, guys, and I'll call it. Is my internet bad? Well, you're out of luck. Let's try. Either Notion is down or my internet is. And it is Notion. Yeah. Oh, there you go. Let's see. Sorry, guys. Oh, no. Oops. Did not reload. This one's still loading. We'll have to call it here, guys. Sorry. These two Notion blocks got missed. Create a thread. If they're super important, create a thread and tag me there. I'll pick it up from there soon enough. Let's call it here, guys. Good class. I'll see you guys tomorrow. We'll be implementing some auto scaling groups in AWS. Maybe doing a bunch of other AWS things. Good night, G.